In this topic, we'll connect PKI, certificates, and trust models to real-world use. You'll see how certificate chains are built, why browsers and systems decide to trust them, and how these mechanisms underpin eIDAS trust services and legally valid electronic signatures. You can think of digital trust as a building, with cryptography as the construction material. Asymmetric keys provide identity and secure key exchange through public-private key pairs. Digital signatures then use those keys to prove who created some data and that it hasn't been altered. Hash functions add compact, tamper-evident fingerprints of that data. Together, these three pillars allow PKI to support millions of users securely, even over completely untrusted networks. Public key infrastructure is really a set of specialized roles working together. The registration authority checks a user's identity and approves certificate requests. The certification authority is the trust anchor. It issues and signs certificates. Those certificates and any revocation information are then published into a repository. Finally, relying parties, such as browsers or back-end services, pull certificates from the repository and validate them before trusting identities or signatures. Within a PKI, certification authorities form a hierarchy of trust. At the base is the root CA. Its key is rarely used, kept offline, and protected as tightly as possible, because the entire hierarchy depends on it. Above the root are one or more intermediate or subordinate CAs. They operate day-to-day under strict certificate policies and CPS documents. And they issue the end entity certificates that servers, users, and applications actually present. Registration authorities are the human and procedural layer that link real-world identity to digital certificates. They check passports, ID cards, or trusted databases, then decide how strongly that person can be trusted online. That strength is called the level of assurance. Only when a person passes those checks is the certificate request approved and sent into the PKI. Once certificates exist, everyone needs a way to check whether they're still valid. That's where repositories and relying parties close the loop. The repository acts like a public bulletin board. It publishes certificates and revocation information such as CRLs or OCSP responses. Relying parties, your browsers, backend services, and signature tools, fetch this data and apply PKI validation logic to decide whether to trust a certificate or reject it. An X509 certificate is essentially three elements working together. First, identity binding. It states who the subject is and how long this binding is valid through the subject name and not before, not after dates. Second, the cryptographic core, the subject's public key plus extensions that define how that key is allowed to be used. Finally, the seal of trust, the issuer's identity and digital signature, which let clients verify the certificate hasn't been forged or altered. Certificate revocation lists try to answer a simple question. Has this certificate been killed early? When a key is compromised, the CA adds that certificate to a large revocation file. Clients don't query about just one certificate. They periodically download the entire list. This batch model introduces delays, bandwidth overhead, and potentially stale information. Until the next download, a client might still trust a certificate that should already be considered unsafe. OCSP lets a system ask, is this certificate still safe to trust right now? Instead of downloading a large revocation list, the relying party queries an OCSP responder about a single certificate. The responder returns a signed status, good, revoked, or unknown. With OCSP stapling, the web server fetches that response in advance and includes it in the TLS handshake, reducing latency while keeping revocation checks trustworthy and current. Every validation process needs a trusted starting point, and that's the root store. It's a curated collection of root CA certificates that your operating system or browser vendor has already vetted. When a certificate chain is checked, the software asks, does this chain end at one of my trusted roots? For eIDAS, those roots must also align with the EU trusted lists. So only qualified trust anchors are accepted for legal-grade trust. A chain of trust is a sequence of signatures linking your certificate up to a root that your system already trusts. The root CA serves as that trust anchor. It signs one or more intermediates, and those intermediates sign the end entity certificates used by servers, users, or services. When a client connects, it tries to build this path automatically, using data inside certificates or local caches, and it only accepts the result if every signature in the chain verifies. When a relying party validates a certificate or signature, it passes through a sequence of strict checks. First, the cryptographic signature is verified against the issuing CA and the chain of trust. Next come constraint checks. Is the certificate within its validity period, and is it being used only for the purposes it was issued for? Finally, revocation information is consulted via CRL or OCSP. If any one of these checks fails, the entire result must be treated as untrusted. Web PKI and eIDAS both rely on certificates and CAs, but they operate in very different worlds. Web PKI is governed mainly by browser vendors, focusing on technical security for HTTPS and general internet traffic. eIDAS is grounded in EU law and enforced by national authorities. Its trust anchors are regulated QTSPs, and the goal is not just secure transport, but legally binding identification, signatures, and cross-border recognition of those acts. eIDAS is the missing bridge between cryptography and real-world contracts. It states in law that a properly created electronic signature can be just as binding as a handwritten one, even across borders. All the PKI, certificates, and HSMs operate behind the scenes, but eIDAS is what turns those technical assurances into legal certainty. All of these pieces connect into one architecture of trust. Cryptography provides the raw tools, and PKI turns them into scalable digital identities. Certificate chains and validation keep that trust intact over time. Frameworks like eIDAS then use this stack to make digital interactions not only secure, but also legally reliable across borders.